Hello again, this is Professor Doug. We are in Chapter 11, Design of Beams and Shafts. In this section, we will actually be looking at how to design to specifications prismatic beams. And we'll look at a couple of examples using Excel. And we're assuming that students of this chapter have read and understood some of the equations needed for beam design, and we will review them in solving our problem sets. The first problem is a prismatic beam of dimensions 6 inches by h. H is unknown, so we're going to be solving for h. But we're also going to be solving for P, the load, maximum load that the beam can support once its h depth is designed according to specifications. And specifications are allowable bending stress, sigma allowable is 1.5 psi, and shear stress allowable is 50 psi. So we're going to enter in all of our information, the beam dimensions, the total length of the span, the allowable tau, and we're going to convert that to KSI from 50 psi. Allowable sigma 1.5 KSI. H, we don't know. We're going to assign 1, a non-zero dummy value, a starter value. The base is 6 inches. That's the same as the thickness. And then P, the load, is also unknown. So this sets up two equations, two unknowns. So it's a perfect problem to use Excel solver functionality, which we will do to solve for both H and P simultaneously. So let's look at the calculations. I, for a prismatic beam, 1/12 BH cubed. So H is basically, it's unknown, so we're going to call it 1. So it would be 1/12 of 6 times 1 cubed, and we get 0.5 inches to the fourth based on this value of 1. Now, if we made the value 2, you can see everything changes accordingly. We're going to leave it at 1. The distance from the neutral axis to the top fiber is h over 2. The section modulus now is a new term. It's I over C. It's defined as I over C. So in this case, I over C would be 1, and it's a cubic dimension. And then we want our Q max. So our Q max, which we've seen in prior chapters, is y bar, which is the distance from the neutral axis to the centroid of the upper portion of the prismatic beam. So that would be h over 4 essentially, which is 1/4 of an inch, based on an h value of 1 again. And then y bar, it was given, it was calculated. Area prime, A prime, is then just h over 2 times 6. So that would be 1/2 times 6, which is 3. So Q max is the multiplicative product of these two terms, A prime times y bar prime. There it is. It's also a cubic dimension. All right, let's skip over to our support reactions. If P is 1 and it's symmetrical, then it stands to reason that AY and BY would be 1/2 kip each. Likewise, if we were to call P 2 kips, those would both be 1 kip, those support reactions. So we're going to keep it at 1. By symmetry, it would be 1/2 of the load at each of the supports. So then we need our Vmax and Mmax. Okay, Vmax, how do we get Vmax? Well, if we were to quickly assess what a shear diagram would look like based on a load of 1, we would have a 1/2 kip up at A, and then nothing horizontally until we get to P. We would go down a full kip to minus a 1/2 kip, and then nothing horizontally until we get to B, and when you go up a 1/2 kip to zero out the shear function, the shear diagram. So the maximum shear at any of these points is still a 1/2 kip. All right, so the maximum moment now is an equation, Vmax times L over 2, which you should learn in this particular unit or earlier in the course. So that's a simple calculation. We're just taking Vmax here times the length over 2. We get 30. Again, this is all dependent on a arbitrarily assigned P of 1 kip, and which ties back to an arbitrarily assigned H of 1 inch. the depth. Okay, so if we assume shear controls our design, tau allowable we know equals Vmax Qmax over IT. Well, we know tau allowable was specified as 50 psi, which is 0.05 ksi. Based on the calculations, Vmax times Qmax over IT, which you see here highlighted, we don't get 0.05, we get 0.125. If we assume bending controls, then sigma allowable equals M max over S. Where did that come from? Well, S we defined as the section modulus I over C. So we know that sigma due to bending allowable is MC over I. So we're just substituting in terms. So it's M max over S. M max was calculated here based on an equation. S was calculated back here based on I over C for the dimension h given or selected. So we know that that should be 1.5 ksi because it was specified. So both tau allowable and sigma allowable were specified, but the calculations that we have produced don't equal these. We want equality on both sides of the equations. So that sets up a perfect situation to use solver to find h and p simultaneously. So what we will do is we will click in this box where it says solver and go to data, solver. Up comes our pop-up window. We're setting that to a value of 0.05 because by equality we should have on both sides of the equations the same answer, and we know this was specified 0.05 by changing the variable cells for h and p because those are both baked into this I equation and Vmax equation, as well as the Qmax equation. The only constant in here is T, the thickness, which is 6 inches. So subject to a constraint. What's our constraint? Our constraint that mx over S also must equal sigma allowable. Here it's 1.5. We got 30 based on our arbitrary selections, so it must be equal to 1.5. So we're going to force it to equal 1.5 by clicking solve. And you can see we went through a couple of iterations here, and our solution is given. Now both sides of the equation are on parity with each other, and h needs to be 8 inches and p needs to be 3.2 kips for a maximum load. So this is a 6x8 design which will support a maximum load, center loaded of 3.2 kips as a point load. The second problem is a little bit more involved, more sophisticated of a problem, perfect for Excel because we have some very nice graphics and we're looking to use a goal seek function to design this beam. So this beam is B by 1.5 B. So the width is B, or the thickness, and the depth or the height is 1.5 B. So we've got two unknowns here based on some function of B. And then we have a triangular increasing load up to the 3-foot distance from A, and then we have 12 kips per foot as a uniform rectangular load from the point where our triangle load reaches its apex to B. Okay, so then we're given sigma allowable, tau allowable. Once again, we're going to enter those in. We don't know what B is. We're going to call it 1. H is then specified as 1.5 times the base. So if we called B 2, then we would get a height of 3, but we're calling it 1. What's the distance from the neutral axis to the upper fiber? It's 1.5 B over 2. So 1.5 B over 2 is going to get us to 0.75. Okay? That's based on, B, again, B is 1, H is 1.5 times B. The length is 72 inches, 6 feet. W sub O starts on the left at A at 0, increases to 12 linearly, triangularly, and then here are our distances. So what are our loads? We want to replace these distributed loads, triangular and rectangular, with point loads. What are the point loads? Well, the triangular one we can do as it goes from 0 to 12 over a span of 3. So that's 12 times 3 is 36. We divide by 2 since it's a triangle, so that's 18. Where do we put it? We put it at 2/3 of the distance from A to the 3-foot mark left to the right of A, it's the centroid of the triangle. So that's 2 feet from A to the right. Then that leaves us with a rectangular load here from the 3-foot distance to B. So that's just 12 times 3 is 36, but we want to replace this with a point load of 36. Where do we put it? Directly in the center between the transition from the triangular load to the rectangular load from that point to B. So it's basically 1.5 feet to the left of B, which is 4.5 feet to the right of A. Okay. Why did we do that? So we can sum moments around A, counterclockwise is positive, and then obviously they're equal to 0, so we want to solve for the unknown by and ay. So these are important because without these we couldn't go on to our next section. So we're not going to do the calcs yet. We're going to go over to the shear and moment calculations, which we've done in the past, now that we know the support reaction. So the support reaction at A is 21. Now we have a triangular load. So we're going to set up an equation here, the shear equation, from point A to essentially midspan is 21 minus 2x squared. Where does this come from? Well, 21 is the support reaction on the left. Then we're going to go down because W is minus the distributed load. But we take 12 over 3. Okay, that's W max, right? 12 over 3. We take 1/2 of that and we multiply it by 1/2 x times x. That's where this comes from. So 12 over 3 is 4. Half of that is 2. 2x times x is 2x squared. So it's 21 minus 2x squared. All right, that's our quadratic equation. And you can see that here from the point A to where we have the 0 crossing. Now the 0 crossing was where we have 0 shear. So if we didn't know where that was, I'm just setting up the equation here, 21 minus 2x squared, okay? And this is the 1/2 12 over 3 times x squared. So that's what this equation is here. So we can really only need to do it once, as you know, right? So we can just do it once here and then copy it down. Okay? Let's just go back there because I think that might have changed. You know, it didn't change. But where we have 0 shear, if we didn't know where that was, let's say we had 3.1, for example. If we were looking for 0 shear, we can set this cell by doing data, what if, goal seek. We can set this cell equal to 0 shear by changing the x value. And that tells us where the 0 crossing is. Okay, it's 3.25. But that's good to know because then for the rest of the shear function, we now have a different configuration of loading, right? So that's going to be from midspan essentially, or 3.25 to the end is 39 minus 12x. Where does that come from? It's just the 0 shear value, 3.25, the x value for 0 shear times W, which is 12. So it's 3.25 times 12, we get 39, right? So if we were to type 0 in here, we should get 39, and we do. Okay, 3.25. So that then is copied down. Again, we can just do it once and copy it down. And now our formatting is a little bit strange, so we're going to go home and format with the paintbrush all these cells. Good. All right, so that didn't quite work out because it should not be so extreme. It should be minus 33. All right, so it's 39 minus whatever the x value is times the load, right? M27. Okay, so what's V max? We want the maximum of this vector, so we can just take the absolute maximum of the absolute value of the vector of shear. We get 33 kips. Okay, that's important. Now, we can plot that here. You have a quadratic up to 3.25 and then linear down to 6. So if we integrate a quadratic, we get a cubic. And if we integrate linear, we get a quadratic. So this is what the moment function looks like. So we can set up a similar type column for moment. And our moment is basically based on the integral of the shear function, right? So we're going to copy this down. And for some reason, I'm losing something in translation here. Maybe I forgot a dollar sign. So I'm not going to worry about it. So what's our maximum moment? We would just want the maximum of the entire vector, right? And we get 45.375. That happens to occur where x is 3.25, and that's the zero shear point. So we learned that previously in the lectures in this section in our course. So if you integrate the shear function, 21 minus 2x squared, you get 21x minus 2/3 x to the third, plus a constant. And if you integrate that next part of the shear function from 3.25 down to the end, then you get minus 6x squared plus 39x minus 18. Where does that minus 18 come from? That's the moment function constant, which is the negative of wx over 2. You can see it here. So all the rationale is explained. So now that we have our max shear and max moment, that's what we need then to go into our calcs. So we wanted to talk about that first. So there's a lot of pre-work to get here. So what's our inertia? Inertia is 1/12 bh cubed based on these non-zero starter values. Our S required should be I over C, and I over C, I was just calculated. C is the neutral axis to the upper fiber, is 1/2 B, 1.5 B over 2, right? And then our base and our height is what we want, because it says determine the smallest dimensions for this beam, B and height, right? Thickness, base, and height or depth to the nearest 1/8 inch, given the ratio. All right, so based on these calculations, we get these large numbers, which can't be accurate, right? That would be feet, many feet in beams. So for this problem, that doesn't make sense. So how do we calculate base and height? Base is M max over sigma allowable times S required. We know all this information, so we can plug it in, and we get 100 inches. And then height is just 1.5 times that. Okay, so we know that this 100 inches is not correct, but it's based on all the prior assumptions of a base of 1 and a height of 1.5 times that base. And you can see those numbers will change if we change our base, right? So the area then is base times height. So what do we want? Tau max, okay, we know, should be equal to tau allowable of 100. It isn't, it's 325. So we can simply go to data. We don't need a complicated solver solution here, just a goal seek. We want to change this value to 100 psi, leave out the units, by changing our arbitrarily selected base of 1. And you can see there'll be some iteration probably, until we converge, and we are converging now at a tau max of about 100 if we get there, and we did. So that's pretty cool, I think, where we're doing all these iterations. We couldn't do that by trial and error. It would be fairly time consuming. So we get our base and our area, and our tau max is equal to what it should be if we had a base here of 18.17 inches and a height of 27.26. So based on our design specs, you can ignore these, right? So those are just dummy starter values. So what we want to do is round these to the nearest 1/8 inch. So based on that, you would go home, number, fraction, and fraction here is something we can probably drop down on the box. And it says we can select a fraction as eighths. There we are, right? So it's 18 1/8 by 27 2/8, which is 27 1/4, gives us an area of 495, and we get roughly equality between tau allowable and tau max, which we should, based on these shear and moment diagrams, which gave us our moment max and our V max, M max and V max. Those numbers are bona fide. Over here, they're used in these calculations. So it's an 18 1/8 by a 27 1/4 inch beam that has a cross-sectional area of 495 square inches. That would satisfy all of our constraints here, allowable bending stress, allowable shear stress, and still meet the base times 1.5 B height or depth specification.